course, I'm going to want you to start by drawing a picture. So here's my little pile of sand that's getting built as this sand is being poured into it more and more. And as I read through the problem and want to start labeling things, the very first thing I encounter is this little tidbit here about the radius being twice its height. So I don't necessarily know how to label that on here at the moment, but I'm just going to go ahead and keep track of that. I'm going to say that the radius is twice the height, like that. So if I multiply the height by 2, I'm getting the radius. All right, and I know that something is growing at a rate of 5 cubic meters per second. Since that's cubic meters, that tells me that it must be a reference to not the radius or the height, but the entire volume of the whole thing. So it's like saying that the sand is pouring into this at 5 cubic meters per second there. All right, and we want to know how fast the height is changing when the height is 10 meters. And so you might be wondering, okay, great, but what's the deal with the radius then? Radius didn't even enter into it, except that it will in a moment here, because we're pouring this 5 cubic meters per second in, and that's changing the volume of this whole deal, which means that the equation we're going to need to write is the volume. And the shape of this pile is a cone, so it's going to be the volume formula for a cone. That is 1/3 pi r squared h. Now, as you saw in the last problem, the first problem that we did with the cone, if I just went straight away to find the derivative with respect to time here, I'd end up with both dr over dt and dh over dt in my final answer. I don't want that. So we need to look at this problem and figure out which one am I actually looking for? Which one do I want? And so in order to answer that question, I look back in the original problem, and what tells me is the question is, how fast is its height increasing? The rate at which its height would be increasing is dh over dt. So that tells me that I want the final answer to include dh over dt. If that final one is going to include dh over dt, that means my equation here should not have r in it. I got to get rid of the r. So I need some sort of equation that then relates r and h so that I can get rid of the r. Look at that. That's what we got right there. We got that r equals 2h. And so I'm going to take that and I'm going to plug that in for r here. And now that I got rid of the r, it's just a matter of simplifying that equation down a little bit to make it a little bit easier to work with. And so the 2 squared gives me 4, which I can go ahead and just put on top of the 1/3 there. And so I got 4/3 pi h cubed. Now we can go ahead and find our derivative with respect to time. And again, before I start going ahead and plugging in values, I'm going to go ahead and clean this up a little bit because like I noticed this 3 here is going to be canceling out with that 3 there. And that should make my life a little bit easier. And at this point now, I can go ahead and start plugging information in. So dv over dt, I know what that is. That's going to be 5. It is a positive 5 because it's increasing my volume by 5 cubic meters every second. And then the 4 pi, of course, stays a 4 pi. And then the h value, my height here, is 10 meters. So that's going to be 10 squared times dh over dt, which remember, that's what we're looking for. So it's good that we aren't finding a value for it right now. And now go ahead and solve that algebraically for the dh over dt. And we end up with a final value of 1 over 80 pi, or about 0.004 meters per second. So we're dumping in 5 cubic meters of sand every second, and yet the height is only going up by this very, very tiny amount, really 4 millimeters per second.